Chapter 5, Atmospheric Moisture and Precipitation. So this unit will get us to a better understanding of the connection between all kinds of things that are changing in our global climate, and the precipitation part of that is enormously important. And by precipitation, I mean rainfall, snow, hail, sleet, and the whole 9 yards. Sometimes I'll just use rainfall, but precipitation is a more encompassing term. So this is a picture or a diagram of the hydrologic cycle. And there's a lot of things going on here. I did choose this one because it has some numbers to it that are kind of interesting to look at. It gives us a sense of magnitudes. There's no number here that's worth memorizing. I can tell you I don't know all these numbers off the top of my head, and neither should you. But let's look at some basics here. And you've seen this cycle, probably you first saw this maybe in middle school, and it shows that we have evaporation that happens not only over the oceans, but where else? If you look at it. So, right, if you look over here, that's over land. And one thing to kind of think about is that you notice that some of the stuff here is italicized, like this one, are italicized. Some are numbers that are just kind of they're expressed after letters that are not italicized, like ice, for example, would be that way. So what are we? And rivers and lakes are that way. So what are we talking about here? Well, the italicized ones, if you look down at the bottom, um, are the flows. So they call that slant font. Okay, I guess that's a simple term for italicized. And then the reservoirs are given in plain font. Okay, and don't worry about the units. I'm just going to call these units here, and later we're having another slide where we're going to talk about this. So these are just units. Okay, so what we see is a huge amount of water tied up in ice. Those are units. And interestingly, if you look at all the rainfall in a year, and this is an annual thing, 113 units versus 26,000 units. So wow, that's kind of an interesting difference. All of the world's land precipitation would take many, many years, and later we're going to calculate that out to equal the amount of water stored in ice. The oceans are a huge reservoir, of course, for water, saline water or salt water. The groundwater, although the biggest number here anywhere on land, is completely dwarfed by the oceans as well. And then, so what happens with the hydrologic cycle? You have evaporation, and then you have condensation over lands and oceans. And the water, some of it comes in snowfall on the mountaintops. And then eventually that some of that water melts and runs off into the rivers and so on. And some of the water also percolates or seeps down into the ground and becomes part of the groundwater down here. Okay. Some of the water runs off on the surface, and some of it will kind of be intermediate. This doesn't really capture that complexity. But in looking at it, you can see that the units here, there's 40 units going this direction, and kind of flow units. And interestingly, ocean precipitation, land precipitation, see there's a big difference. There's more than triple over the oceans. That shouldn't surprise us either. Okay, so hopefully you're getting a little sense of it just by me talking about it, kind of how it works. Of course, where's the energy for that evaporation? It's the sun, right? We talked about that before. And there's a huge amount of heat transfer by evaporating water and then condensing it somewhere else. We actually bring energy to land from the sea because when we have condensation, at least the air over the land warms up a little bit from the condensation. So that's the basic diagram. What I have now are some facts relating to the previous slide about this. And one is just that a huge amount, as we said, of all the water, fresh water, is in the form of underground water or ice. and less than 1% of all fresh water is found in lakes, rivers, and other available surface forms. So as we have more people in the world and more uses per person, which tends to be the case as societies get wealthier, we have more pressure on fresh waters. So a couple questions for you. I'm not going to give you the answer to these in my presentation here with this unit, but later you'll discover it on your own, and you'll see why as we go through this. So there's one, and then there's another question there. And what I want to do is share with you some interesting facts about average residence time for water molecules. The oceans, a water molecule in the oceans has a residence time somewhere between 3,200 and 4,000 years on average. Of course, some waterfalls, rainfall on the oceans and evaporates the very same day. Others, water ends up in the deep oceans for tens of thousands of years. So, there's always a huge range, but this gives us some sense of an average. Scientists don't know exactly what that number is, but this kind of gives us a ballpark there. Atmosphere. 9 days. Wow. Yeah. So from the time water is evaporated and then is precipitated out, the average residence time is 9 days. That's amazingly short overall. And of course, we could find examples of that being even shorter. Soil. So rainfall penetrates into the soil. Some of it later is evaporated right back out when it's hot. Could be very short order, or could be there a year, in some cases even more, but this kind of gives you a kind of a typical range. And all of the world's precipitation, all the world's soil moisture is roughly the same amount. But in some areas of the world, of course, the very wet rainforest, there's an excess of precipitation. Others, there's a deficit. So it depends on where you are. Even here in Oregon, I mean, the Oregon coast is wetter than, or the higher mountains is wetter than, say, places like John Day or some other areas of the interior. So it varies widely. And the biosphere, living organisms, average residence time for a water molecule is about 1 week. So even our human body, right? So I drink water. Some of it stays in my, about 70% of me water is water. And some of that I'm literally breathing out as water vapor right away. Other stays in my blood and other organs and so on. So there is a wide range of that, but kind of typically about a week there is with plants or animals. It gives you a broad average. So what I want to show you now is a map that if you just look at it in the middle, this is the Americas. Then we have Asia over here and Australia, Africa over on the right side, Europe. So this is a map of the world, Antarctica down below, and the Arctic in the north, Greenland here, so on. But what this is it's evaporation minus precipitation. Okay, so in the hydrologic cycle, this is enormously important, and it relates to the previous slides. In that, if you look at amazingly, the subtropical oceans, especially the kind of tropical, except for right at the equator, because this is basically the equator right across here, okay? This is the equator, just to give you a sense of ground. It should be about halfway between the north and the south part, right? About halfway down. That's the equator. And you can see roughly straddling the equator, there's this enormous region where the numbers are greens and blues and even purples. These are areas where there's more precipitation than evaporation. So there are areas of where a lot of the moisture is just literally in a huge surplus. But really, those areas of the world of huge surpluses are pretty small. Now, bordering out, as you can see, you go from these blues, which are big surpluses down below. These are all surpluses. And then when we get into the subtropical Pacific, wow, all the way across the subtropical Pacific, the Atlantic, and roughly the same latitudes in much of the southern hemisphere, in the tropics, subtropics, it's deficit. These are dry areas. So the yellows, oranges are dry. In other words, even though they're oceans, there's way more evaporation going on in those oceans than there is precipitation. And so that evaporation means that we're tying that solar heat up, and a lot of that moisture is then brought into other areas. Some of it just cycles right back into the equatorial area and rains. But also, as we noted, the westerlies will carry a lot of this moisture up into, for example, our own west coast and into the interior. Same with Europe. The westerlies will carry a lot of the moisture into Europe here. And so this evaporation, big evaporation basins, basically the subtropical and even kind of middle latitude oceans are really giant evaporation basins carrying moisture later onto land for us. So this gives you some sense. If you look in our own Northwest area, you can see by and large, we are a surplus area on the west side of the Cascades, and then going on the other side, it gets drier. You can kind of see that. It's pretty much all the way up into Canada that way, a little bit into California. But if you look at the U.S. as a whole, think about this a little bit. The big question for you later on this. If you look at the U.S. as a whole, there is largely in the northern Mexico as well, we're mostly places of either the white, which is kind of a break-even number for the case of the Americas, or we're a deficit. Much of the Great Plains is a light deficit. The Southwest entirely deficit areas. And again, this white color here usually means somewhere between 0.2 and negative 0.2. But there are some areas where we don't have real good data, so they just are blacking those out. Obviously, we know the Sahara is an area of deficit. That's not a surprise. So it's either no data or somewhere in this range here. So there are a few places in the world where we just don't have good enough data, even though it's pretty easy to estimate what those might be. All right, so enough said on that. The summary I should have put this up here before I talked about it, but as you look at this later, you'll kind of see this and just think a little more about these. Okay, but an amazing pattern. Much of the middle latitudes and up are areas of surplus. No surprises because there's not as much heat, so not as much evaporation, and you have the westerlies and the subpolar lows with their rainfall for a good part of the year here. And down here, it's the same way. But wow, the tropical and subtropical ocean basins, with the exception of the ones nearest the equator, are areas of deficit. Okay. Now, evaporation. What influences evaporation? That last map, half of the theme was really all about evaporation. What influences that evaporation? So this is something, middle school kids are usually pretty good at these kind of factors on up. And you intuitively know some of this. For example, when you come out of a shower and you walk into a room, if you haven't totally clothed yourself yet, ooh, you feel that chill right away, okay? Relative humidity is lower when you get outside the bathroom, for example. Or in the summer, the way we stay cool is that we evaporate water when we're exercising. And so summer, notice I said. So the temperature must have something to do with that, right? So let's look at these. So temperature is one, and the basic relationship is the warmer the temperature, the higher the evaporation. And later we're going to leave this on a more detailed scale, but I just want to put these 3 points on this slide. Second one is wind. So you just run through a sprinkler and you stand there and on a windy day, you get chilled right away. But if it's not a windy day, maybe you don't get chilled so quickly, right? So the evaporation rates are accelerated by wind. The more wind, the more evaporation. And then finally, relative humidity. The higher the relative humidity, in other words, the more humid the air feels to you, the lower the evaporation rate. So in other words, the lower the relative humidity, the drier the air feels, the higher the evaporation. And the evaporation rates are what keep us cool. So as humans, we like to live in areas of low relative humidity in our summers if we can, so we're comfortable. Okay, and that's why the Pacific Northwest, excuse me, has some of the most comfortable summers anywhere, because we have lower relative humidity. And a lot of that's just because we have a cold ocean nearby, by the way. And we don't tend to have really strong direct flows from the ocean over large periods or large regions. But even when we do, because the ocean's cold, it doesn't have a lot of moisture there that imparts to the air as it travels over the ocean and to us. Okay, so this then brings us to our next slide, and I'm going to go ahead and do this on the next edition. So we'll see you in a bit.